Good morning, everyone. Today we will read Chapter 5 Bioinorganic Chemistry of Pradeep Publication Volume 3. Inorganic chemistry deals primarily with salts and complex metal ion, where bioinorganic chemistry deals majorly with inorganic chemistry when applied to biological systems. Thus, bioinorganic chemistry can be regarded as the branch of science that relates inorganic chemistry with life processes by recognizing the role of a metal ion in the normal growth and function of biological process. In brief, bioinorganic chemistry highlights the role of metal ion in biology. Bioinorganic chemistry is a rapidly developing area of chemistry because it is important in biological system. The essential biological roles of a few elements have been known for many years. This chapter will focus on the important roles of metal, non-metal, and their compounds in biological processes. 5.1 Essential and trace elements. We think that the chemistry of life is solely composed of organic molecules. It is a wrong concept. In fact, there is a long list of inorganic compounds that are essential to living systems. For example, the skeletal and integumental material outer covering in higher animals is composed majorly of inorganic material, and the lifetime consumption of oxygen by a living entity is a major fraction of its material need. In addition, water, oxygen, calcium phosphate, and calcium carbonate are the major inorganic constituent of living matter in terms of quantity. Of all the known elements, it is about 30 elements that have been recognized as essential and indispensable to life. Of the 30 elements, 15 of them are metals. The essential elements are needed for the growth and normal function of animals and plants. Absence of these elements results in severe malfunction of living organism. Thus, an element may be considered essentially when its insufficient intake produces an impairment of normal function and its restoration relieves the impaired function. Some of these elements are required in bulk or macroscopic amount of all the form of life and are classified as bulk elements. Some of the bulk elements are required for structural purposes, that is, skin, bones, eggshell, various organs, while the rest are used in minerals. In the other words, in the absence of essential elements, the organism can neither grow nor complete its full life cycle. The essential elements can be further subdivided into two groups. First, bulk elements, essential elements that are formed in higher concentration, and trace elements, essential elements that are present in low concentration. Bulk quantities of group 1 and 2 metals are required mainly to balance the electrical charge associated with the negative charged macromolecule in the cell, and it is also to maintain the osmotic pressure inside the cell. The reaction flask of a given living organism is the cell. In addition, the transition elements, the heavier member of the P group, also play an important role in bioinorganic chemistry. Some of the inorganic elements are required in small quantities and are classified as traces or ultra traces elements. These different types of essential elements present in the living system are classified in Table 5.2. It is important to note that all the elements displayed in table 5.2 are required by the plants and animals. For example, sodium ion Na positive is of a special importance to higher animal. It is, however, not essential to many bacteria and plants except blue-green algae. The ultra trace element, that is boron, aluminium, vanadium, are needed by some higher plants. Molybdenum is essential only to those organisms which deprive their nitrogen from inorganic source. Selenium is an essential micronutrient for mammalian species but proved to be toxic at higher level. Selenium deficiency in human result in a degenerate condition of heart tissues known as Kishan disease, named after a county in China, in which it was endemic because extremely low selenium levels in the soil coupled with a population that entirely depend upon local grown grains. It is important to note that even some essential elements may prove to be toxic if consumed in large quantities. 5.2 Essential bulk elements. Sodium and potassium. We have learned that both sodium and potassium are essential for life processes. For example, we need at least 1 gram of sodium ion per day in our diet. However, because of our habits to adding salt on food, some people consume as many as 5 times more than required. However, intake of potassium is not a problem. Instead, potassium deficiency is more common. We must include potassium rich foods such as banana and coffee in our diet. In inorganic chemistry, we always think of the similarities between sodium and potassium. However, in biology, it is difference between sodium and potassium which play important role. Cell pumps out sodium ion of the cytoplasm whereas cells pump the potassium ion inside. This ion sodium transport is sometimes called as a sodium pump, and it involves both the active expulsion of Na positive ion and the active take up of K positive. It is the difference in the total alkali metal ion concentration inside and outside of the cell that produces an electric potential across the cell membrane, which is important for the functioning of nerves and muscle cell. The transport of ions require energy, and this is obtained by the hydrolysis of ATP, adenosine triphosphate. It is estimated that hydrolysis of ATP molecule to ADP, adenosine diphosphate, provide enough energy to move 3 Na positive ions out of the cell and 2 K positive and H positive ion back into the cell. Calcium and magnesium. Both calcium and magnesium present in the body fluid, Mg2 positive ion are concentrated in the animal cells and Ca2 positive ion are concentrated outside the cell. This is similar to the presence of K positive ion inside cell whereas Na positive ion outside the cell. Ca positive ions are present in the external skeleton of creatures such as shellfish and corals. The material used is calcium carbonate. Creatures with the interior skeleton such as mammals and reptiles use calcium hydroxide phosphate Ca5OHPO4 whole 3 and the enamel on the teeth as fluoropeptide 3 bracket Ca3PO4 whole twice CAF2. Both these compounds are highly insoluble. Important minerals used in biological material are listed in table 5.4. Ca2 positive ions are important in blood clotting and are required to trigger the concentration of muscles such as those that control the beating of the heart. In fact, some types of the muscle cramps can be prevented by increasing the intake of calcium ion. A decrease in Ca2 positive content of blood, either due to dietary deficiency or from an insufficiency of the parathyroid hormone, may lead to a disease called tenaty. On the other hand, an increase in the concentration of Ca2 positive ion in the blood may lead to the calcification of several internal organisms. The absorption of dietary Ca2 positive and Mg2 positive ion from the intestinal tract may be prevented by stimulatious indigestion of dietary Ca positive is greatly affected with the other constituent of the diet. Both Ca2 positive and Mg2 positive ion are excreted mainly by the large intestine instead of kidney. Magnesium, because of its high charge radius ratio and consequent strong hydration, as in Mg H2 whole 6 2 positive, plays important biological role that are different from those of calcium. It acts as a counter ion to the negatively charged group in nucleotide and polynucleotides. One of the most important nucleotide is ATP, adenosine triphosphate, which serves as a fundamental energy source for the living cell. ATP is thus known as energy-rich molecule. It is used to derive most of the chemical reaction of the cell. Mg2 positive ion from a complex with ATP has been observed all that transphosphorylation reaction involve ATP proceeds smoothly in the presence of Mg2 positive. ATP is an anhydride of phosphoric acid. The hydrolysis of anhydride is a very favorable reaction. Thus, hydrolysis of ATP to ADP, shown in the equation below, liberates 30.7 kilograms per mole of energy at pH 7. The living system thus utilizes this energy to derive energy requiring biochemical processes. It has been observed experimentally that the activation effect of Mg2 positive ion transphosphorylation may be duplicated in vitro by Mn2, Ce2 positive, CO2 positive, Zn2 positive, or Ni2 positive. The most important aspect of the biochemistry of magnesium is its role in photosynthesis. Magnesium contains chlorophyll. Using energy from the sun, converts carbon dioxide and water into sugar and oxygen. 6CO2 plus 6H2O gives C6H12O6 plus 6O2. Without the oxygen from the chlorophyll reaction, this plant would still be surrounded by a dense layer of carbon dioxide. In addition, without the sugar energy source, it would have been difficult for life to progress from plants to animals. It is important to note that magnesium ion sits in the middle of the chlorophyll molecules and hold the molecule in a specific configuration. Magnesium has only one possible oxidation number plus 2. As a result, the electron transfer reaction involved in photosynthesis can proceed without interference from metal ion. Phosphate. Phosphorus is an important element for life processes. For example, free hydrogen phosphate PO4 3 negative and dihydrogen sulfate H2PO4 negative ions are involved in the blood buffering systems. Phosphate is the linking unit in the sugar ester of DNA, deoxyribonucleic acid, and RNA ribonucleic acid. The phosphate unit make up the part of ATP, the essential energy storage unit in living organism. Bone is the phosphate material, the common called mineral apatite in calcium hydroxide phosphate, CaFiOHPO4 whole thrice. The process of phosphorus in bones and its function is called in regulation of pH of blood constitute an important feature of phosphate. It is important to mention that the normal formation of bones depends upon the relative amounts of dietary phosphorus and calcium in addition to vitamin D. 5.3 Essential trace elements. Among the known trace elements, the three most prominent biologically active metals are iron, copper, and zinc. The remaining trace elements, except boron and fluorine, are used in very small amounts, less than 10 mg in adult human, and are referred as ultra trace elements. The trace elements are known to play important role as metal enzymes. Iron is essentially in small amounts for both plant and animal life. However, like copper and selenium, it is toxic when used in larger quantities. Biologically, iron is the most important transition element and is found in the greatest abundance in biological system in the form of the porphyrin complexes or hemins such as hemoglobin and myoglobin. Porphyrines are microcyclic ligands and are deprived of porphyrin discussed later. A human body weighs around 70 kg contain about 4.3 gram of iron. Nearly 70% of this iron is present in hemoglobin and about 3% in myoglobin. The remaining 23% of body iron is present as ferritin. Ferritin is present in spleen, liver, and bone marrow. It consists of a shell of linked amino acids, peptides called as apoferritin surrounding a core of iron 3 oxohydroxophosphate. The core is a cluster of iron 3 ions, oxide ions, hydroxide ions, and phosphate ions. And the composition FeOOH8, FeOPO3H2. It is very large, containing up to 4,500 iron ions. With its hydrophilic coating, the large aggregate is water soluble and is concentrated in the spleen, liver, and bone marrow. Apoferritin protein can be prepared from ferritin by reduction of ferric ions or ferrous ions at pH is equals to 4.5. followed by the removal of Fe2 positive by dianalysis. The molecular weight of apoferritin is nearly 46,500. Ferritin can also be synthesized in the laboratory with properties similar to the natural ferritin. It can be prepared by treating crystalline apoferritin with an inorganic Fe2 salt in the presence of oxygen. Ferritin is probably formed in vivo by an analogous process. The various steps involved in the pathway of Fe2 positive from the foodstuff to hemoglobin and to ferritin involved in the following process. First, the Fe2 positive of the bound dietary material is reduced to Fe2 positive in gastrointestinal tract. Second, after absorption into the cell of the intestinal mucosa, Fe2 positive is incorporated into ferritin as Fe3 positive. The Fe2 positive in mucosa is also converted into Fe3 positive plasma, bounded by the iron binding globulin named transferrin. Fourth, plasma Fe3 positive is in equilibrium with iron in the liver, spleen, and bone marrow. Zinc. Among the trace elements, zinc is second only to iron in importance. Zinc is essential to all organisms and play important biological role in the enzyme system of an animal and plants. Humans contain about 2 grams of zinc and it's one of the most important and crucial elements in our diet. Deficiencies of zinc are not life threatening but contribute to fatigue, lethargy, and related symptoms. Zn2 positive ion is a soft except compared to other divalent ion that Mg2 positive, Ca2 positive, or Mn2 positive and act as a strong Lewis acid toward many biomolecules. Compared to Zn2 positive ion, Cu2 positive ion is also soft but has an addition intermediary oxidation state, that is Cu positive. Different oxidation state of copper may allow different redox reaction and complicate its behavior. The complex of zinc ions Zn2 positive are much more liable than the corresponding complexes of Mg2 positive, Ni2 positive, or Mn2 positive. This felicitates the role of zinc ion in enzymes. Since Zn2 positive ion is completely resistant to redox changes and biological potential, its role cannot be affected by changing the redox potential in the organism. A number of enzymes containing zinc ion are known. The importance of all the enzymes in the carbonic anhydrase. It is present in red blood cells and is involved in respiration. It speeds up the absorption of carbon dioxide by red blood cell in muscles and other tissues. On the other hand, in the reverse reaction, it involves releasing of O2, CO2 in the lungs. The reaction is pH dependent. CO2 aqueous plus H2O and equilibrium gives H2CO3 aqueous. Thus, the zinc containing enzymes carbonic anhydrase catalyzes the otherwise slow carbonic acid carbon dioxide equilibrium reaction. The carbonic anhydrase has a common four coordinated environment around Zn2 positive ion in which three of the ligands are imidazole nitrogens of 3 histidine and the fourth is a water molecule or hydroxide ion as shown below. As water molecule coordinated to a zinc ion has the peak Na7 and thus the role of a zinc is to reduce the basicity of hydroxide ion such that a high effective concentration of hydroxide can exist in approximately neutral medium. Another important enzyme containing Zn2 positive ion is carboxypeptidase. It is present in the pancreatic juice and is primarily involved in the digestion of proteins by animals and protein metabolism in plant and animals. This enzyme catalyzes the hydrolysis of terminal peptide amide link at the carboxyl end of the peptide chain. The enzyme is selective and works only when the R group in the terminal amino acid is aromatic or a branched aliphatic chain has L configuration. Copper. Copper is the third most biological important transition metal after iron and zinc. Human being needs around 8 mg of copper daily. A deficiency of copper, then the optimum value results in the inability of animals to use iron stored in the liver. As a result, the animals suffer from anemia. The copper is bound to protein in the human either as metamonoprotein as or as enzymes. Excess of copper is highly poisonous, particularly to fish. This is the reason it is always advised not to throw copper coins in fish pools for good luck. Human beings can excrete any excess of copper, but a biochemical defect can result in copper accumulation in the liver, kidney, and brain. The illness caused by the excess of copper is called Wilson's disease. It is a hereditary shortage of ceruloplasmin causing copper accumulation in the liver, kidney, and brain. Patients suffering from Wilson's disease are cured by administering ethylene diamine tetraacetic acid (EDTA), which forms soluble copper complex. The soluble copper complex can be excreted harmlessly through urine. At the same time, many other essential metals involving in other enzymatic reactions from EDTA complexes and are excreted. Thus, EDTA treatment can upset many unwanted enzyme reactions. As a result, utmost care should be taken in monitoring Wilson's disease. Hemocyanin is a copper containing protein which is important as an oxygen carrier in some invertebrate animals. Despite its name, it is non-heme protein. It is found in the blood of snail, crab, lobster, octopuses, and scorpions. The oxygenated hemocyanin are blue colored, unlike human blood, and have one dioxygen molecule attached to two copper atoms. Deoxygenated hemocyanin contains Cu1 and is also blue. Selenium. Selenium is an essential to health. All classes of organisms metabolize selenium. In human and other mammals, saccharose disease arises from either the excessiveness or insufficient dietary selenium. The toxic effect of some plants accumulate large amount of selenium as methylselenocysteine in order to keep selenium away from the metabolic machinery. Animals that graze these selenium accumulation plants developed severe toxic reaction including blind staggers and alkali disease. Selenium poisoning in human is rare but has occurred where mines have caused selenium to be leached from the soil into drinking water supplies. Loss of the hair and nail is seen in the human selenium toxicity followed by anemia and jaundice. Although selenium is toxic at high levels, selenium is essential micronutrient from mammalian species. Selenium deficiency in human resulted in degenerative coordination of the heart tissue known as Cation disease. Disease is named after a county in China. The accepted minimum daily requirement of selenium for adult is 70 microgram. Many types of food provide selenium, particularly seafood, meat, grain, and the onion family. Mammals and birds require selenium for production of the enzyme glutathione peroxidase, hydrogen peroxidase, and organic peroxidase, which cause oxidative damage to cellular components, are enzymatically destroyed by this selenoprotein. Such antioxidant activity suggests that glutathione peroxidase and therefore selenium protect the oxidation induced cancers. Chromium and molybdenum. Trace amounts of chromium and molybdenum are necessary in the diet of mammals. Chromium 3 and insulin are both involved in maintaining the correct level of glucose in the blood. A deficiency in chromium 3 or inability to use chromium 3 ion results in the removal of glucose from the blood as fast as normally and leads to diabetes. Compounds containing chromium 6, example dichromate or chromate, where ingested or absorbed through skin, are carcinogens. Therefore, utmost care must be taken while using K2Cr2O7 or K2Cr2O4, especially Performing titration. Molybdenum is the most commonly important member of the chromium family. It is the highest atomic number element to have a wide range of functions in living organism. The most important molybdenum enzyme, which contain iron as well, is nitrogenase. Thus, nitrogenase contain two protein, that is molybdoferrodoxin and azoferrodoxin. Molybdoferrodoxin is air sensitive and brown colored species containing two MO atoms, 24 to 36 Fe atoms, and 24 to 36 S atoms together with a protein. It has molecular weight of about 2,25,000. Azoferrodoxin is yellow air sensitive, is a derivative of peroxidine Fe4S4 SR4 whole 4. It has a molecular range from 50,000 to 70,000. The enzyme nitrogenase occurs in bacteria and reduces the inert dinitrogen of the atmosphere to the ammonium ion. This reaction is used in the synthesis of protein by the plants. Let us have an idea of importance of this enzyme by the typical example. The amount of dinitrogen fixed biologically is estimated to be 175 million tons per year compared with the total 110 million tons of NH3 produced by hybrid wash process and distillation of coal. Question 1. Why is metal are rare as molybdenum so biologically important? There are several reasons to address this question. First, molybdenate ion MO4 2 negative has high aqueous solubility at near neutral pH values, making it easily transportable to the biological fluid. The iron has a negative charge, making it more suitable for different environments than are cations of period for transition metals. Third, the element has a wide range of oxidation state +4, +5, +6, whose redox potential overlaps with those of biological systems. Fourth, being a soft Lewis acid, molybdenum 6 shows a strong bonding preference for the soft Lewis bases. Sulfide, another important example of the enzymes. Nickel. The biochemistry of nickel is poorly understood of all the four period transition elements. It is present in some enzyme system in the form of porphyrin type complexes. Some of the tropical trees concentrate nickel to such an extent that it makes up nearly 15% of their dry mass. It is highly toxic to most plants and moderately toxic to animals. Calcium. Cadmium is a toxic element that is present in our foodstuff and is normally indigested at levels that are close to maximum safe level. Kidney is the organ most susceptible to cadmium. Cadmium is indigested close to maximum safe level. Kidney is the organ most susceptible to cadmium. Cadmium indigested 200 ppm cause severe damage. Cigarette smokers absorb significant level of cadmium from tobacco smoke. Exposure to cadmium from industrial source is a major concern. Use of nickel cadmium battery is becoming a major waste disposal problem. Many reputed companies are now accept return and use nickel cadmium batteries so that cadmium metal can be safely recycled. Mercury. Mercury is hazardous because it offers relatively high vapor pressure. The mercury vapor is absorbed in the lungs, dissolved in the blood, and is then carried to the brain. This causes irreversible damage to in the central lungs, dissolves in the blood, and then carried to the brain. This causes irreversible damage to the central nervous system. In it is slightly soluble in water because of very weak metallic bonding. Inorganic compound of mercury are less toxic as they have solubility in water. Arsenic. Arsenic is an essential element to life. However, we need ultra trace amount of this element. Anything more than a tiny amount causes arsenic poisoning. Arsenic in measurable quantities caused death through enzyme inhibition. Non-metals. The non-metals among essential elements are hydrogen, carbon, oxygen, nitrogen, phosphorus, sulfur, chlorine, and iodine. Majority of these are needed in trace amount except carbon, hydrogen, nitrogen, and oxygen, which are abundantly available and constitute most of the chemicals in the living earth system. Phosphorus. Phosphorus is an essential element for life. It constitutes an important part of energy-rich molecule known as ATP, adenosine triphosphate. It is also an important component of bond as apatite. CA5PO4 whole 3 OH, that is calcium hydroxide phosphate. Partial formation of fluoroapatite CA5PO4 whole 3F strengthens the structure of the teeth and make it less soluble in the acid, forming the fermenting organic material in the teeth. Iodine. Nearly 75% of the iodine present in the human body is located at one place, that is the thyroid gland. It is used in the synthesis of hormone thyroxine and triiodine thyroxine. These hormones are essential for growth, for the regulation of neuromuscular functioning, and for the maintenance of male and female reproductive functions. One of the most cause goiter is lack of iodide in the diet. A symptom of goiter is the swallow lower part of the neck. The enlargement is the attempt of a thyroid gland to maximize absorption of iodine in iodine deficient circumstances. In order to remove iodine deficiency, potassium iodide is added to the common household salt. Such a salt is known as iodized salt. Chloride ion. The chloride ion has a vital role in the ion balance in our bodies. It does not appear to play an active role but simply act to balance the positive ions of Na positive and K positive. It is a major anion found inside and outside the cell. It is essentially an SNaCl electrolyte for higher mammals and plants. Chloride ion is essentially in digestive juices. Deficiency of chloride ion in infant leads to impaired growth. Nearly 30 elements are now recognized as the essential elements for at least some of our lives. It includes most of the elements through atomic number 35 except for BeAl, SCTI, GeOGe. Along the noble gases, molybdenum and iodine are also essential. It is interesting to note that the element appreciably abundant in human body are also abundant in seawater, suggesting without that doubt of the family tree has rooted in the sea. 5.4 Metallophorphins. Phorphins constitute an important class of bioinorganic compounds in which a metal ion is surrounded by 4 nitrogen of a phorphine ring. Phorphins are microcyclic tetradentate ligand made up of 4 pyrrole rings together through methane bridge as shown in figure 5.1. This tetradentate ligand has a conjugated double bonded system with 4 nitrogen donor sites. Two of the 4 nitrogen are tertiary nitrogen, while the remaining 2 are secondary nitrogen. The tertiary nitrogen atom also coordinate bonds by donating pair of electrons, such each to the metal ion by a coordinate bond shown by the arrowhead. The other two second nitrogen lose a proton each from a covalent bond with metal ions as shown. Thus, a porphyrin ring serves as a tetradentate di-negative ligand. As a result, the di-positive cations like Fe2 positive, Ni2 positive, or Mg2 positive will form a neutral complex with phorphins, which in the process loses 2 protons shown in the figure. When 4 pyrrole rings of a porphyrin are substituted by organic groups other than hydrogen, it is called a porphyrin. Thus, porphyrin are microcyclic tetrapyrrole system with conjugated dibonds together with various groups other than hydrogen substituted at the periphery of the ring. The substituent attached to the ring are usually organic groups with electron withdrawing or electron releasing characteristic. The complex formed by the porphins with the metal ion, generally di-positive, are called metallophorphins. These are biologically important compounds and play a very important role in the animal and plant kingdom. Phorphins ring system is fairly rigid because of the delocalization of electrons in the molecule. Although the skeletal structure is fairly rigid, significant variation has been observed among the metallomorphins in the interatomic distance between the pyrrole nitrogen and the metal ion at the center, determining the size of the central hole. From a knowledge of the covalent bond radii, one can estimate that a bond between a nitrogen atom and an atom of the first transition series should be 2.0 Armstrong log. In brief, the ideal size of the atom to fit in a hole is 2 Armstrong. Thus, the size of the hole in the center of the porphyrin ring is ideal for accommodation metal ion of first transition series or lighter alkaline earth metals. A metal ion of appropriate size sitting at the center of the porphyrin ring will surrounded by 4 nitrogen of the parole and forming a square planar geometry. It means that the metal ion 4 nitrogens lie in the same plane as shown as figure 5.1. However, when the size of the metal ion is smaller than the ideal, the ring will be reluctant to accommodate precisely the metal ion. In this way, the ring will either readjust or distort itself in order to accommodate the metal ion. On the other hand, the size of the metal ion is larger than the ideal. The transition metal ion cannot fit in the hole and stays out of the plane of the 4 nitrogen atom. It means that the metal ion sits above the plane of 4 nitrogen atom and acquires square pyramidal geometry. The nature of the metallophorphins vary with the temperature of the metal ion and the type of the organic group attached at the eighth position of the 4 pyrrole ring around the periphery of the porphins. A group related compound, the phthalocines shown in figure 5.2 are isoelectric with polyporphyrins. These compounds are of interest because of their intensely colored metal complexes, which are of utmost commercial application in dyes and pigments. The size of the hole in this thylacines ring is about 0.1 Armstrong smaller than in porphyrins as a result of nitrogen atom compared with carbon. Compare the covalent radii of carbon 0.77 Armstrong and nitrogen 0.75 Armstrongs. Two of the most important metal complexes of porphyrins are chlorophyll and heme. These are being discussed. Chlorophyll is a magnesium complex of porphyrin which plays an important role in photosynthesis. Photosynthesis is a remarkable redox reaction in nature that converts water and carbon dioxide into sugar and oxygen in the presence of sunlight. CO2 plus H2O gives C6H12O6 plus 6O2. This process is the primary source of food that we eat and the molecular oxygen that we breathe. The function of chlorophyll molecule is to absorb photon in the red part of the visible spectrum, 700 nanometer, and pass this energy of excitation to other species in the reaction chain. The ability to absorb the light is due to the conjugated polyene structure and the porphyrin ring structure system. The role of the magnesium is to make the entire molecule rigid so that the energy absorbed is not easily lost. There are a number of similar bond but not identical chlorophyll molecules. It is important to note that in chlorophyll A, the basic porphyrin sister has been modified in two ways. In pyrrole ring 4, one of the double bonds has been transhydrogenated to form a magnesium dihydroporphyrin complex. In addition, a cyclopentadiene ring has been fused to the side of the pyrrole ring 3 as shown in figure 5.3. In brief, absorption of sunlight by chlorophyll is the first step in the conversion of sunlight into usable energy by plants. It will not be out of place to say that chlorophyll are nature's solar energy collectors. Heme is an iron 2 porphyrin which is present in hemoglobin and myoglobin which is being discussed. 5.5 Hemoglobin and myoglobin. Molecular oxygen play an important role in biological system because of its importance in respiration. The formation of oxygen we have already learned involved in nature involves a number of reactions such as redox reaction, electron transfer, atom transfer, and photochemical reaction. A number of proteins are known that bind and transfer oxygen to different extents. Such proteins that bind oxygen are called oxygen carriers. The most important and well documented protein that bind and transfer oxygen are hemoglobin and myoglobin. Hemoglobin and myoglobin are very closely related to each other. Hemoglobin is a larger protein with a molecular mass of 64,500 and consists of 4 subunits. Each subunit is made up of heme group associated with the protein called the globin. It is important to recall that the each heme group is composed of Fe2 positive ion surrounded by 4 nitrogen of a polyphenol ligand. Hemoglobin is a large intracellular protein that is responsible for the red color of the blood cell. On the other hand, myoglobin is a relatively smaller protein with a molecular mass of nearly 17,000 and consists of one heme group and a polypeptide chain. It is important to recall that the peptide chain consists of 150 to 160 amino acid residues folded about single heme group. Myoglobin is small intracellular protein in a vertebrate muscle. Myoglobin was the first protein whose X-ray structure was established in 1959. In 1962, the Nobel Prize in Chemistry was awarded to Kendrew and Schultz for their work on the structure of globular protein, including myoglobin. The basic functions of hemoglobin and globin are the following. First, hemoglobin picks up oxygen in the lungs and transports it to the rest of the body. Second, myoglobin accepts oxygen from the hemoglobin in the muscles and store it until it needed for the energetic processes. Third, deoxygenated hemoglobin uses some of the amino acids to fix up CO2 and then transport CO2 back to the lungs. Oxygen carrier perform the function of the acquiring O2 from the atmosphere, transporting it through the circulatory system of the organism and delivering it to the location where it is used. They all bind O2 rapidly and reversibly according to the equation 5.1, that is protein plus O2 in equilibrium with protein O2. The equilibrium must be largely to the right at the oxygen concentration available at the pickup location. For example, lung air interface, muscle cell body interface, and mother fetus interface at the placenta. It is important to note that the oxygen carriers interact strongly with the oxygen to bind it. However, the carrier must not undergo the irreversible process in the oxidation in the process. In brief, hemoglobin picks up oxygen in the lungs and transport it to the site of the inside the muscle cells. The oxygen is transferred to the myoglobin, which stores it until required for metabolic action, in which O2 is reduced to CO2. Deoxygenated hemoglobin then transports CO2 back to the lungs. Structure of hemoglobin and myoglobin. We have already mentioned the structure of hemoglobin and myoglobin are very closely related to each other. Hemoglobin is a large protein and consists of four subunits. Each subunit contains one heme group associated with the protein globin. The iron is held in a position by coordination and the nitrogen of heme and an imidazole of globin complex. The complex reversibly with oxygen is shown as figure 5.4b. Thus, hemoglobin is the oxygen carrier of blood and the red color of the blood is due to the oxygenated hemoglobin. It is important to note that the four sites units are similar but not identical. Two subunits from alpha chain of 141 amino acid while other two subunits from beta chain of 146 amino acid. These chains are coiled together to give a three-dimensional network. A systematic structure of hemoglobin showing the relationship among four subunits of the tetramer is shown in figure 5.5. Structure of myoglobin. Myoglobin is a small protein compared to hemoglobin. It consists of a single heme group embodied in a polypeptide chain called globin. The peptide chain consists of 150 to 160 amino acid folded about a single heme group as shown in figure 5.6. The heterocyclic ring system of a heme group consists of a polyformic containing pyrrole group labeled as ABCD, linked by methane bridge. The iron atom in the oxidation state to Fe2 present at the center of the heme is bonded by 4 nitrogen of the porphyrin system together with 1 nitrogen of the imidazole side chain of the histidine residue, which is a part of a long chain protein chain of amino acid residue. It is the polypeptide chain that plays an important role in the biological fixation of molecule dioxygen. A simple outline of the structure of myoglobin is shown. Heme group embedded in polypeptide chain is shown in figure 5.6. It is important to note that both hemoglobin and myoglobin have 5 coordinated iron atom. The oxidation state of iron in hemoglobin and myoglobin is +2. Iron atom is bonded to 4 nitrogen atom from the pyrrole ring or porphyrin and the fifth nitrogen from the protein chain. In both the compounds, the sixth position is occupied is weakly bonded to water. Hemoglobin and myoglobin in such molecule are named as deoxyhemoglobin and deoxymyoglobin respectively. However, when the molecular oxygen occupies the sixth position, which is trans to histidine chain, then the molecules are named oxyhemoglobin or oxymyohemoglobin respectively. A myoglobin polypeptide is comprised of eight separate rings called handed alpha helix designated from A to H that connect by short non-helical region. Role of hemoglobin and myoglobin. Hemoglobin and myoglobin play a crucial role in transporting dioxygen O2 from lungs to tissue and CO2 as HCO3 negative from tissues to the lungs. The function of hemoglobin is to bind O2 at the higher oxygen partial pressure found in the lungs tissue to form HbO2. Hemoglobin carries this oxygen without loss through the blood and then releases it to the myoglobin. In other words, the dissociated oxygen from hemoglobin diffuses to the tissues where myoglobin picks it up and stores it until it needed. It means that myoglobin has greater oxygen affinity than hemoglobin at lower partial pressure. The hemoglobin and the carbon dioxide CO2 as HCO3 negative are then returned to the lungs where CO2 is exhaled. It is clear from the scheme 5.2 that both hemoglobin and myoglobin play a cyclic role in transporting O2 from the lungs to the tissues and CO2 from the tissues to the lungs. The CO2 carried out in the form of HCO3 negative ion. CO2 plus H2O gives H positive plus HCO3 negative. Carefully analysis of the scheme suggests that the partial pressure of O2 is high in the lungs, about 100 torr. This is responsible for the formation of HbO2. However, lower partial pressure of the O2 in the tissues 20 to 30 torr is responsible for the dissociation of HbO2. The dissociated oxygen O2 diffused into the tissues and oxidized the metabolic fuel to CO2 and H2O. The carbon dioxide evolved with exhaled in lungs. Oxidation and oxygenation of Hb and Mb. The heme group consists of Fe2 positive ion embedded in a porphyrin ligand. The Fe2 positive ion has six coordination sites. The porphyrin ligand takes up only four of these six sites, leaving two free binding sites on opposite sides of the metal ion. If a free heme is present, in aqueous solution, the two vacant sites may be occupied by the water molecules. In an aqueous solution containing oxygen, a free or naked heme group binds to the oxygen molecule is an irreversible manner with the oxidation of Fe2 positive or Fe3 positive ions. This oxidation of the iron from Fe2 positive and Fe3 positive destroys the oxygen binding of the activity of iron. This unproductive oxidation in a biological system is heme Fe2O2 water gives hematin Fe3. Potential fatal. This unproductive oxidation in biological system is potentially fatal. The irreversible oxidation of free heme in the presence of oxygen involves a series of dimerization containing two Fe3 ions, Fe3 ions, Fe3O, Fe3 as shown in figure 5.7. This dimer is known as hemactin. The dimer can no longer act as oxygen chimer. Deoxymyoglobin deoxy-MB is a 5 coordinated high spin Fe2 complex T2G4 EG2 with 4 of the coordination site of iron being occupied by the 4 nitrogen of the phosphorus ring, while the fifth coordination site is occupied by the nitrogen atom of the imitative ligand of histidine residue which joins the heme with the protein. In the absence of O2, the ligand field is weak and such 5 coordinated heme complexes of Fe2 are always high spin. The diameter of high spin T2G4 and EG2 Fe2 ion is larger than the center of the hole of the porphyrin ring. The estimated FeN bond distance is about 218 pm in high spin Fe2 complexes, while the size of the whole of the porphyrin ring is about 200 pm. As a result, the iron 2 ion is compelled to 0.40 Armstrong above the plane of the ring formed by the 4 nitrogen atom to give a square pyramidal arrangement, thus distorting the bonds around the iron as shown as figure 5.8. When oxygen bonds at the 5th 6th position of iron opposite to the histidine, the Fe2 positive ion contracts and moves to the plane of the ring. In other words, Fe2 positive ions become coplanar. This happens because the moment the oxygen gets coordinated to Fe2 positive, the ligand field becomes strong, which results in spin pairing. You recall the spin pairing always leads to low spin complexes. This in this case, the electronic configuration of iron 2 ion changes to T2G6 and then resulting complex is diamagnetic. The FEN bond distance is approximately 200 pm, which matches the size of the whole of the porphyrin system as shown in figure 5.9. It is important to note that the binding molecule dioxygen to the sixth position of the iron atom in the dioxy hemoglobin or deoxymyoglobin releases the strain in the 5 coordinated system. This releases in the strain is compensated by the loss of the spin pairing energy in going from 5 coordinated deoxyhemoglobin deoxymyoglobin to 6 coordinated oxyhemoglobin myoglobin respectively. It means that the coordination of O2 will cause Fe atom to drop into the plane of the heme group. The shrinkage of the if shrinkage in the size of Fe2 positive ion and dropping into the plane of the porphyrin ring is shown in figure 5.10. The dropping of Fe2 positive ion in the plane of the porphyrin results in the perturbation in the imidazole group of histidine residue present at the transposition. In other words, the decreased size of the Fe2 positive ion is sensed by the imidazole group of the histidine residue, which behaves like a spring. In doing so, Fe2 positive moves the histidine molecule and cause conformational changes in the globin chain. Since the chain is hydrogen bonded to the other three units, it changes their conformations as well as the net effect on this interaction in hemoglobin is the increase in the ability to attract O2 to the second heme sites and so on. It means that one iron binds an oxygen molecule, the molecular shape changes to make the binding of additional oxygen molecules easier. Since each heme group is hemoglobin can bind one oxygen molecule, the process continues till it carries a maximum of 4 molecules of oxygen. The phenomena is called cooperative effect or autocatalytic nature of O2 binding. 5.6 Myoglobin and hemoglobin function and cooperativity. The function of hemoglobin is to bind molecular oxygen O2 at the high oxygen partial pressures found in lung tissues and then carry it without the loss of the blood to the tissue where myoglobin picks up oxygen from hemoglobin. The sequence indicates that myoglobin has a greater O2 affinity than hemoglobin at lower partial pressure of oxygen. 5.7 Nitrogen fixation. There is a large amount of N2 gas, 78% in the atmosphere. However, plants are not able to utilize this N2 because of its relatively unreactive nature. The unreactive nature of dinitrogen is ascribed to its very high bond strength, 945 kJ per mole, due to the presence of a triple bond between two nitrogen atoms. Soil that are very fertile contain nitrogen in the form of nitrates, NO3 negative, nitrites, NO2 negative, ammonium salts, NH4 positive, or urea, NH2CONH2. All these compounds are absorbed from the soil water through the roots of the plants. The continuous uptake of nitrogen by plants reduces the fertility of the soil. In order to fix nitrogen, that is to make nitrogen reactive towards the other substance to produce nitrogen compounds, it is necessary to use energy rate conditions. This process of conversion of atmospheric nitrogen into useful compounds such as ammonia is called nitrogen fixation. In 1965, Cesar Sanoff, a Canadian research student at the University of Toronto, was studying the reaction of ruthenium 3 chloride with hydrazine hydrate. He synthesized a brown compound by combining ruthenium 3 chloride with hydrazine hydrate but was unable to explain the chemical composition of the compound formed. One fine day, during a discussion with another chemist, he got an idea that this brown compound formed. One fine day, compound form may be contain dinitrogen bonded to the ruthenium metal similar to the bonding of the carbon monoxide. With the transition metal, he reported this exciting news to his supervisor, Bjorn Allen. After several months, Sanoff and Allen submitted the manuscript of their research finding a journal for publication. The manuscript was rejected because dinitrogen is known as to be able to inert as noble gas. However, Sanoff and Allen again appealed to the editors of the journal. The editor sent the revised manuscript to 16 other celebrated inorganic chemists for the comment, and they all agreed with the discovery, and the research paper was published. As a result, the world of inorganic chemistry was changed, suggesting that the dinitrogen is no longer unreactive, and the first compound of dinitrogen was born. The first dinitrogen compound of dinitrogen can be readily prepared from aqueous ruthenium 3 chloride using hydrazine hydrate in aqueous solution. The pentamine dinitrogen ruthenium 2 cation RuNH3 whole 5 N2 2 positive was formed and could be isolated in a variety of salts. Today, almost all the transition elements are known to give dinitrogen complexes, and more than 200 such compounds are well characterized. Several new methods have now been found in the preparation of complexes containing pentamine dinitrogen ruthenium 2 cation. A direct method involving nitrogen as involves the prior reduction of pentamine ruthenium 3 salt with the zinc amalgam as RuNH3 whole 5 Cl2 positive react in the presence of ZnHgH2O gives RuNH3 whole 5 H2O 2 positive. RuNH3 whole 5 H2O 2 positive plus N2 gives RuNH3 whole 5 N2 2 positive pale yellow plus H2. The strong nucleophilic nature of dinitrogen group is shown in the above reaction where coordinated water is easily displaced by gaseous dinitrogen. Another interesting example of the strong nucleophilic nature of the dinitrogen is shown by the formation of bridged complex. RuNH3 whole 5 N2 2 positive plus RuNH3 whole 5 H2O 2 positive gives RuNH3 whole 5 N triple bond N RuNH3 whole 5 4 positive plus H2O. Another general method of for the preparation of metal complexes of dinitrogen involve the reduction of the metal complexes, especially of molybdenum and tungsten, in the presence of suitable co-ligands under N2. Example: MOCl4 PME2PH whole twice plus N2 react in the presence of N-toluene or PME2PH gives cis MON2 PME whole PH whole 4 WCl4 plus PME2PH whole twice plus N2 reacts with NaHg and PME2PH and gives cis WN2 PME2PH whole 4. Some of the other examples are FeClH, DPE whole twice plus N2 in the presence of NaHB for Me2CO gives trans FeDPE whole twice HN2 plus NaCl. NiACAC to give 4PCY3 plus N2 in the presence of ALME thrice gives NiN2 PCY3 whole twice. DPE is equals to diethyl phosphinoethane. ACS is 3,5 pentanedione and PCY3 is equals to tris cyclohexyl phosphine. Dinitrogen can coordinate to the metal in four ways shown below. However, end-on modes are well not exemplified in structure 1 and 2. The formation of stable dinitrogen complex led to the study with other transition metals. Complexes with titanium 2 are most promising. It has been found that titanium 2 alkoxide can be easily reduced with the subsequent release of the ammonia or hydrazine, a complete cycle of reactions depicting the fixation of atmospheric dinitrogen to ammonia is reported below. An X-ray study of RuNH3 whole 5 and 2 positive complex indicates that RuNN linkage is a linear in a very related compound where the coordinate is triphenylphosphine. The molecular structure is shown in figure 5.11. The CONN linkage is almost linear with an angle of 178. The bonding in N2 complexes resemble that of carbon monoxide complexes. Back bonding of electron density from metal to into pi antibonding orbitals is clearly reflected in the shortening of CON bond 1.807 Armstrong, which is closer to COCO bond 1.753 Armstrong than the CONH3 bond 1.95 Armstrong in amine complexes. The NN bond length 1.112 Armstrong is longer than found in molecular dinitrogen. Molecular nitrogen 1.098 Armstrong, suggesting a weakening of nitrogen-nitrogen tripole bond from the electron density in the antibonding orbital of nitrogen. Compare the value of 1.116 Armstrong for bond order 2.5 for N2 positive. Over several hundred compounds of molecular nitrogen with transition metal are known today. This new discovery of stable metal dinitrogen complex led to extensive investigation of the possibility of fixation of nitrogen. In other words, major interest lies in converting metal N2 complex with appropriate reducing agent to convert N2 into ammonia under ambient conditions. Dinitrogen transition metal complexes MONW have been shown to protonate the coordinated dinitrogen into diazine H and double bond NH isodiazine NNH2 hydrazido NH and NH2 or hydrazine H2 and NH2. For example, trans Mn2 whole twice DPPE whole twice plus HX at 20 degrees Celsius gives Mn2H2 DPPE twice X2 plus N2, where M is equals to MO or W, X is equals to halide, and DPP is diphenyl phosphonoethane. The reduced product N2H2 has been assigned the diazine structure H and double bond NH. It acts as a 2 electron donor. All attempts to reduce N2H2 further to N2H4 or NH3 by using stronger reducing agents have met with success. On the other hand, dinitrogen metal complex with the monodentate co-ligands have successfully monodentate co-ligands dimethyl phenylphosphine on treatment with H2SO4 in NaOH, followed by the distillation afforded high yield of ammonia with trace of hydrazine. Mn2 whole twice P Me whole twice pH4 plus H2SO4 in the presence of CH3OH 20 degrees Celsius and distillation N2 plus 2NH3 plus pH Me whole twice pH plus M4 products, where M is equals to MO and W. In case of tungsten complex, the yield of ammonia evolved has been found to be quantitative, whereas only 66% of ammonia is evolved in case of the corresponding molybdenum complex. In case H2SO4 is replaced by hydrogen halides, the intermediate isohydrazine complex is formed, which upon substituent reaction with H2SO4 in MEOH followed by the distillation F4 ammonia is shown above. Cis Mn2 whole twice PME2 PH whole 4 plus HX in the presence in MEOH gives MNH2 PME2 PH whole thrice plus N2 plus PH Me2 PHX, where M is equals to MOW, X is equals to ClBr or I. A similar reaction of trans Wn2 whole twice PMePH2 whole 4 with HCl in methanol liberates. The chemistry of molybdenum and tungsten has been extensively studied. A reasonable mechanism of these reactions is outlined in the scheme. A careful inspection of the reactions cited above reveals that the fixation of N2 to NH3 in these stable N2 metal complexes involve the replacement of CO ligands such as tertiary phosphines, which stabilize the N2 metal complexes involves the replacement of CO ligand such as tertiary phosphine, which stabilize the lower oxidation state with anion ligands such as halide or sulfate, which stabilize the higher oxidation states. This process promotes electron transfer from metal to N2 or dinitrogen hydride and finally to ammonia. In order to fix nitrogen, this is to make nitrogen react with other substances. Several nitrogen fixation bacteria are known that are able to convert dinitrogen N2 to NH3 under mild conditions, that is, under ambient temperature and pressure. This venture is highly profitable in view of the huge stores of nitrogen available in the atmosphere that can put up use for chemical use both for agricultural and industrial purposes. Metal- Metalloenzymes have been found to play a key role in such processes. So, this is it for the chapter 5 Inorganic Chemistry Pradeep's volume 3. Thank you.